My name is Victoria Shpekovich, and today I would like to discuss with you the potential of plasmon-assisted microscopy of nano-objects, PAMONO technique, for diagnostic and treatment of COVID-19 and other viral pathologies. This is joint lecture which I prepared together with my colleague from Technical University of Dortmund, Konstantin Wüsterfeld. And the first part of this lecture will be devoted to details about PAMONO-sensor instrument by itself. And in the second part of this lecture, Konstantin will discuss questions associated with software development for PAMONO-sensor. Just let me introduce shortly myself. I'm a biologist and currently I work in the Leibniz Institute for Analytical Sciences, ESAS, with a PAMONO-sensor as a bioanalytical instrument. And we try to develop different assays based on the PAMONO-sensor for detection of viruses, virus-like particles, and other biological nanovesicles, for example, extracellular vesicles. As you already noticed, this is joint project. ESAS develops instrument, PAMONO-sensor, and our colleagues from Technical University of Dortmund help us developing software. And this project is a part of SFB 876, where we work together. And this project currently is a transfer project. This means we work together with companies which plan to provide us real biological samples for analysis. And now I would like to describe theoretical basis of plasmon-assisted microscopy of nano-objects. This is SPR, surface plasmon resonance-based technique. On this slide, presented the most common scheme of the surface plasmon excitation. In this scheme, p-polarized incidence laser beam passes through the glass prism coated with gold thin film. And thus, passed beam can be reflected and detected by CCD camera. However, it was noticed that at particular angle of incidence, the beam is not reflected any longer, and total internal reflection occurs. In this case, at this particular angle, which has name resonance angle, the energy of photons of the laser beam is transformed in the energy of free electron gas, which exists in noble metal film, in gold film. Such situation leads to creation of very sensitive reflection conditions, So any changes in the close proximity to the metal surface, adsorption of small particles or molecules can lead to the changes of reflection conditions. And if before absorption no reflection occurred, after absorption, as you may see on the scheme, reflection occurs once again and can be detected. On the right panel of this slide, you may see typical image of the binding signal after binding of biological or non-biological nanoparticle to the sensor surface. So typical image consists of gray background, no reflection, and very bright spot. The binding event occurred and reflection condition changed. Reflection occurs also. Reflection can be detected by CCD camera. Over here, you may see also so-called step signal. This graph represents changes of intensity during the measurement time. First, intensity oscillates at the particular level. Then, binding event occurs. Intensity jumps and stays on the new level, oscillating on it, as you may notice on the graph. Both the image of binding signal as well as step signal, intensity step signal, are characteristics of the binding event detected by PAMONO-sensor. They both serve for the development of software which we use for the detection of binding events by the PAMONO-sensor. I also would like to mention that instead of coating the prism surface by gold or other noble metal, one may coat glass plates with the same refractive index as a prism with thin metal film. It is better since it makes easier the substitution of optical parts. It is easier to change glass plate coated with thin film than to change prism. And you will be able to see these gold chips as well as general optical setup of the PAMONO-sensor in the next movie. Today, I would like to demonstrate you optical and mechanical parts of the PAMONO-sensor. And also, I would like to show you small, however very important parts of this instrument. For example, now you may see gold sensor chip. This chip consists of SF10 microscopic glass plate which is coated by two metal layers. The first one, the adhesion layer, is the layer of titanium which has 5 nanometer thickness. The second one is gold sensing layer, and this gold film has thickness around 50 nanometers. The size of this chip is 9 to 13 millimeters. Normally, we use exactly such chips in our routine detection of biological or non-biological nanoparticles. And now you may see prism which is already mounted with flow cell. So this is the prism and this is the flow cell. You also may see the piping system. This is inlet and outlet tubing. So this is exactly the heart of our PAMONO-sensor. And now let me show the elements of our PAMONO-sensor. You may see over here laser, in our case this is a red laser, with the wavelength 675 nanometers. This laser serves us as the source of the light. Laser beam comes onto this mirror and it is reflected and passes through the polarizer, which is located over here. Polarized light is the pre-requirement for the plasmon wave excitation, which occurs into the gold film of our gold sensor chip, and which actually serves as a basis for the detection of viruses and virus-like particles by our sensor. Then the beam comes to this mirror and is reflected to the heart of our sensor, to the prism connected with flow cell, which contains gold sensor chip. Exactly over here, the analyzed sample passes through the surface of gold sensor chip, and particles of interest, viruses or virus-like particles, have an opportunity to bind with sensor surface of our PAMONO-sensor. The reflected light passes through the objective, which is located over here, and this is normal photo objective, and further reflected light can be captured by CCD camera. As you may see, the PAMONO-sensor is a rather simple and portable instrument. And now I would like to mention differences between classical SPR approach and our PAMONO-sensor. Certainly, SPR sensors were known in biology for a rather long time before PAMONO-sensor was developed in our institute. However, these SPR sensors actually were able to detect the formation of layers of biomolecules on the sensor surface, as you may see, for example, over here. And the intensity increased upon formation of films of biomolecules on the sensor surface. So they were not able to detect the binding of individual nanoparticles, such as viruses, virus-like particles, or extracellular vesicles. In the case of PAMONO-sensor, the situation is different. In spite previously it was mentioned that SPR-based sensor cannot detect the binding of single viruses or virus-like particles. Theoretical opportunity for such detection existed, and after certain technical improvements, it was possible to develop sensor which actually can detect binding of individual viruses or virus-like particles. And why we're telling that we detect binding event, not see the particle by itself, and why we actually can mention that this picture is the image of binding event, just because of the explanation provided over here. When particle binds to the sensor surface, such binding causes secondary plasmonic waves, and in spite particle by itself causes just very small distortion in the main plasmon wave, secondary plasmonic waves, which expands in the metal film, they have a micrometer scaling. So a nanometer particle causes signal which can be distinguishable, causes secondary plasmonic wave, and this wave has micrometer size. That's the reason why a nanometer particle looks for us as a micrometer signal. And because we see binding event, not particle by itself, so it is not the image of the particle. It is the image of binding event. We cannot tell anything about the shape of the bond particle. However, we may tell a lot about the size of the bond particle. To this issue, I will return a little bit later. And I would like to mention which types of particle PAMONO-sensor may detect. As you already heard, we work with non-organic particles made out of polystyrene, silica, and metal particles. With metal particles, we may work with so small particles as 40 nanometer easily without any problems. We only need to keep in mind that particles supposed to be charged. Among biological particles, we already worked with microvesicles, so with a group of extracellular vesicles, and with those particles which are especially important for us, with viruses and virus-like particles. The difference between viruses and virus-like particles is rather simple. Viruses contain genetical material, virus-like particles lack this material, and because of that, virus-like particles cannot reproduce themselves. They are not dangerous. They mimic by their surface viruses. They contain all proteins and all other molecules on their surface which resemble the surface of viruses completely, but virus-like particles are not dangerous. They cannot replicate. And that's great, because they can serve as a very nice model for our studies. We may work with something with virus-like particles which possess surface equal to dangerous viruses, but are not dangerous. And now I would like to demonstrate the movie with an image sequence of 200 nanometer polystyrene particles recorded during PAMONO-sensor detection. So on this image, two different regions are visible. The region where signals from 200 nanometer particles are focused, and the region where they are non-focused. Focused regions, upper part of image, they are very bright, and unfocused signals, they contain dark spots in the center of binding signal. So for the future, it would be important for us to expand the area of the detection. Currently, we can detect only those signals which are focused. We count them, and this helps to quantify target particles in the sample. However, in the future, we hope to be able also analyze signals which are in non-focused area. And now I would like to talk about possible ways for gold sensor surface functionalization in order to perform specific detection of target viruses in the analyzed sample. There are many possible ways. Just only two of them presented on this slide, and I would like to concentrate on the right one. When we use protein AG coating of gold sensor, followed by a coating of anti-target antiviral antibodies. Thus, we have the situation when specificity of our detection strongly depends on the specificity of antibody which we use. The benefit of this method is the possibility of elution already captured viruses or virus-like particles for further analysis by other methods. I also would like to mention shortly bioanalytical features of the PAMONO-sensor. First of all, we found linear dependency between a signal counting rate and the number of particles in samples. We demonstrated this for non-organic and for biological particles. This feature helps us to measure concentration of viruses or virus-like particles in the sample upon appropriate calibration of our PAMONO-sensor. We also noticed that influence of serum on the detection of virus-like particles is rather small till relatively high concentration of serum in solutions. Thus, PAMONO-sensor can work in complex biological matrices with complex biological samples. We also proved the specificity of detected signals using two different types of virus-like particles, those with ovalbumin on the surface and those without. In this experiment, gold sensor surface was covered with antibody against ovalbumin, and the difference in detection of over-containing in comparison with over lacking virus-like particles, as you may see, huge. We also demonstrated the ability of PAMONO-sensor to size nanoparticles which exist in sample. We compared this ability of PAMONO-sensor with a commercially developed LM10 device based on the principle of nanoparticle tracking analysis. And as you may see, our PAMONO-sensor at least is not worse than LM10 instrument in the separation of different types, different groups of nanoparticles in mixtures, and also in sizing of monodisperse mixtures. I also would like to mention that the main feature of the PAMONO-sensor is its ability to provide label-free but specific detection of individual viruses and virus-like particles. PAMONO-sensor is a relatively simple, cheap, and robust instrument, and it can not simply quantify viruses, but also analyze their size distribution. Measurement time, and this is important, measurement time of the PAMONO-sensor depends on the concentration of viruses in analyzed samples. So if you have very concentrated sample, particles will diffuse to the sensor surface relatively fast. And if the concentration is rather low, it will take longer to detect particles in analyzed sample. In some methods, time for particle quantification does not depend on the concentration of particles. PAMONO-sensor represents a sensing platform with high versatility. So one instrument may combine several functions. And let's compare these features of PAMONO-sensor with the current requirements to the tests and sensing device which suppose to detect SARS-CoV-2 virus in different samples. What may be expected from such device? This instrument is supposed to be fast, simple, reliable, and cheap. Indeed, PAMONO-sensor is a rather simple, reliable, and cheap instrument. It really may help to analyze samples provided by relatively large groups of people, travelers in airports, trains, students in schools and universities. So what is the position of PAMONO-sensor among other tests which are currently available? DNA amplification method, polymerase chain reaction, is the most common for the detection of viral nucleic acids in samples. However, this method cannot provide information about immune status of the patient. The next type of methods are lateral immunoassays. They help to detect antibody against virus in patient samples. Indeed, they are simple and relatively fast. However, they cannot work with pooled samples. PAMONO-sensor can detect viral particles by themselves and also can detect antibodies against viruses. In the next slide, I will explain how this can be done. As you may see, plasticity of PAMONO-sensor is based on the different functionalization of the gold sensor chip. On the panel A, you may notice that gold sensor is functionalized with antibody against spike protein as protein of COVID-19 virus, and in that case, we just will detect virus particles by themselves. In the case of functionalization of the gold sensor surface with spike protein, synthetic spike protein, we will be able to detect immunoglobulins or molecules which bind to spike protein. If we are interested in the immune status of the patient, then scheme C, panel C, illustrates the way how to do that. Spike protein will be located on the gold sensor chip. Immunoglobulins M or G will bind spike protein, and then they will be detected by antibody conjugated with gold particles, antibody against immunoglobulins M or G. And in order to investigate interactions between spike protein of virus and its counterpartner on the cell surface, HCE2, the same strategy may be used. Spike protein will be located on the gold sensor surface. HCE2 will bind with spike protein, and antibody against HCE2 conjugated with gold particle will interact with HCE2. Thus, PAMONO-sensor enables specific detection and quantification of viruses in samples. It also can help to detect antiviral antibody, providing information about health status of the patient. Upon calibration, PAMONO-sensor helps to size viruses and other biological nanoparticles. Moreover, functionalization with protein AG permits to elute captured viral particles and perform their further analysis. And before my colleague Konstantin Wüstefeld will continue our joint lecture, I would like to mention challenging tasks which appeared during software development for the PAMONO-sensor. First of all, we would like to perform automatization, the controlling of PAMONO-sensor settings, such as speed of the pump, objective focusing, rotation of the prism. It also would be nice to have an opportunity to perform reliable detection of viruses, not only in focused areas of the images, but also in unfocused zones. That will help us to detect very low concentrations of viruses or other biological nanoparticles in samples. And certainly, it would be very important to have an opportunity to detect viruses and other biological nanovesicles in very noisy image sequences. I also would like to thank all of our colleagues who helped us to make PAMONO-based studies. People from different universities and working groups. And now Konstantin will continue our story about software development for the PAMONO-sensor.
Welcome to the second part of the PAMONO-sensor presentation. My name is Konstantin Wüstefeld and I'm a member of the project B2, and I will tell you something about how we can detect nanoparticles from the recorded PAMONO-sensor images. At first we will start with the goals we have for our detection pipeline. We want to detect particle sizes between 80 nanometers and 200 nanometers. we want to have a special robustness against disturbances. If we imagine that we will use this device in front of football stadiums or airports, we have to expect a lot of vibrations and external influence. There could also be dust particles in a sample, so we have to consider that as well. And the gold plate could also be imperfect, so this is we could call it an internal reason for disturbances. We would like to have a fast detection and keep the needed user input low, so in the best case everyone should be able to use the device. One thing that would also be nice is that we can make use of older recordings. This means we have a lot of recordings that are quite old and were recorded with a slightly modified device, so maybe the camera has changed or other things in the hardware. And we don't want to throw away these old recordings, but use them for training of the neural network. So if we have a look at the database we get, here's for example one raw image, but rather a raw image stream. So we can see exactly what the camera records from the reflected laser. We see that there's a very strong background and we only see slightly changes and cannot really tell where some particles attach and where not. So this is modeled in this signal model. We have an intensity I, which represents the intensity of a pixel at x, y position, and we have a background signal that is multiplied with our particle signal, so the signal we look for, and an artifact signal. This artifact signal is basically a disturbance. At last we have a noise signal which is added to the signal. So the next step will be that we will try to remove the background. There will be two variants of it, the global preprocessing and the local preprocessing, and we will see the benefits of both. So we start with the global preprocessing. The global preprocessing assumes that we have a constant background over time. So we calculate the first, we call it here the first S frames, and we calculate a pixel-wise mean over time. So this pixel-wise mean will conclude the background. In the second step, we will divide each pixel of the following images by the mean pixel from the first step. The result of this will be corrected with a constant value, so we just add some value to each pixel to make the image more bright. Below you can see the result of that. So this is the raw image from one slide before, which was modified with this term. And we can see that some particles appear like this region or this region, and they attach for a long time until the end of the recording. The second variant of preprocessing is the local preprocessing, where we'll use a sliding window to iterate over our stream. If we imagine to currently look at frame P and have a window size W given, then we will calculate the pixel-wise mean for the W half frames before P and the W half frames after P. The result will be that we gain two aggregated images, one for the future pixels and one for the past pixels. After that, we can divide the future pixels by the past pixels for each place in the image. So, and when we think about it, intensities which increase over time will have a rather high value, while intensities that stay the same over time or decrease will become a low value. After that, we will clip values below a specified value. The specified value will be, in our case, the median of the current picture we look at, multiplied with a factor. This factor could be, for example, 0.1, and we will cut off every pixel that is really dark. So we assume that this is some rest noise we have in the picture. After that, we use a histogram stretching. That means that we will use all values of the representation area and gain a high contrast in the image. The result looks like this. So this is the same recording as I showed you before, but now pre-processed locally. We see that we have a really big difference between the particles and the background. If we have a look at this, not at the spatial component, but at the temporal component, we can take one pixel and display this graph over time. So we can see that the noise really looks like noise in this case, and one particle which attaches generates a high difference, a clear difference over time in the globally preprocessed variant. When, for example, two particles attach, we also can distinguish it from one particle. In the locally preprocessed variant, it doesn't look that nice. The noise and the particle are not that clearly distinguishable from each other. As well, one particle and two particles attaching are not really different from each other. So if we just want to see if the temporal signal belongs to a particle or not, the globally preprocessed variant will be the variant of choice. We look at the spatial components again and see this comparison side by side. We see another difference of the preprocessing variants. While the particles stay attached in the global preprocessing images, the local preprocessing images contain particles which vanish over time. The reason for that is not that they really detach again, but that they will become part of the local background. This is the thing that makes it difficult to determine whether it's a particle or not on the temporal side, but it becomes a lot easier over time to detect new particles. While the image above is full of particles, we cannot really tell where a new particle attaches. In the local preprocessing variant, this is no problem. So the global preprocessing is better for temporal detection, and the local image is better for spatial and visual detection. This also holds for the creation of annotations, for example. One drawback can be that through the local histogram modification we can increase flicker effects. After we saw that both preprocessing variants have advantages, we of course want to profit from both of them. In our complete detection pipeline, we will use the windowed preprocessed data for spatial recognition, while the globally preprocessed data will be used to check on a temporal basis. At first, we will have a look at the spatial prediction network. Our spatial prediction network is basically a mask RCNN. This mask RCNN receives separate images. This means that each image will be analyzed independently from each other image. The output which we receive are bounding boxes, a mask for each bounding box, and a confidence value that a particle lies in this bounding box, respectively in the mask. The model parameters allow us to define the allowed proposed region sizes and scale factors, so we can define how large or how small a particle has to be seen as a particle of interest. The training is done on a ResNet 50 FPN, so on a feature pyramid network, which was already pre-trained on the COCO dataset. This has the advantage that many features are already learned, which can be adapted to our problem. After we saw how the spatial predictions are made, we will now have a look at the temporal filter. The temporal filter receives the bounding boxes and masks from the spatial predictor and the globally preprocessed images. So when we receive such a mask, which we can see here, the red polygon represents the mask, so everything inside this polygon will be belonging to the mask. And we transfer this to the globally preprocessed images. As the assumption is that the particles of interest stay attached, we can extract such a curve, and we see that such a curve belongs to a particle. We take n frames from this graph around a particle candidate and analyze it in a temporal filter network. This network consists basically of 3 fully connected layers with a leaky relo activation and a dropout which is used just for training. The output is a particle of interest classification, so we get a confidence of how probable it is that the analyzed graph belongs to a particle. The training is done on an equal number of positive and negative sets, so a negative example would be a random mask that is placed anywhere in the background of an image. The Gaussian noise is added to add a certain diversity in the data. The last thing we have to look at in terms of the temporal filtering is the improving of the generalization capability of our network. So, as already mentioned, the lightness can vary locally. A disturbance which is imposed on the device can introduce a region with brighter intensity, although that is not belonging to a particle. When a particle then appears in that region, it's difficult to say if it's a particle or not. This can be improved when we relativize the lightness for each candidate region. After the spatial network, we have this mask available, and we then calculate the mean of the mask pixels and divide it by the mean of the background pixels. And the background pixels are the bounding box, maybe an extended bounding box around this mask. And the result is that the feature which is calculated is independent of the local background. Another thing is that the lightness can vary in each data set. So this graph, for example, is just belonging to one particle in one data set, and it starts at 125. For another data set, it could be that most of all, for another particle size, this graph starts at another position, so maybe at 110. To prevent that our network learns the absolute heights of these values, we normalize the vector to lie in between 0 and 1. Having a look at our detection pipeline, we can see that there's one module left. This module is the trace generator, which receives input from the spatial prediction network and the temporal filter. And as you may have noticed, we currently have predictions for each single image, but we do not have a connection between the detections. The trace generator will establish such a connection as it collects candidates on consecutive images and merges it to a sequence of candidates. In a second step, we will filter out short traces, which may come through short disturbances. and we will filter up gaps in the traces, as there can always be some missing detections. We will smoothen the result. The total particle count will in the end be the number of result traces. Now we can also have a look at the trace generator calculations a bit more detailed. So the first step is the creation of traces. And two candidates J1 and J2 are collected into one trace if they have an IOU value, which is an intersection value of the overlapping area, higher than a given threshold, and if they are close enough together on a temporal basis. So if the frame of J1 and the frame of J2 are close together. This closeness value is meant to bridge some gaps. So if we have a long trace of particles lying at the same position and there are some missing frames in between, we tolerate them as we see that there can be errors in the processes before. In the second step, the filtering of short traces will take place by looking at the maximum frame and the minimum frame that we have in our sequence. If the difference is high enough, we keep the trace. If it is too low, then we delete it. The third step will fill up the gaps. So this is no error to display it in this way. We have slightly different positions of boxes in following frames. And if we have a gap in between, we will interpolate the bounding box border points, these 4 border points, by looking at the 2 edge boxes. So the result will be a smooth transition also within this gap. Now I want to demonstrate you the result of the trace generation. In the upper part of the video you will see the candidates before the trace generation, and in the lower part you will see it after the trace generation. If you closely look, you can see that some flickering is at particle detections, which is smoothened in the video below, and there are some candidates which are filtered out. I've also provided some other result videos so that you see that there are slightly different characteristics. So the first video is the detection of a high amount of particles. So this is a rather high area and a rather high concentration of particles per area. The lower detection video shows one sample with relatively low concentration and some interesting wave effects which can be seen in the upper left corner. And the pipeline bridges some of these disturbances, as we can see here. After you gain some insight into our detection pipeline and the visual results, I want to quantify them a bit. So what we did was that we trained and adjusted parameters on 2 datasets with 200 nanometer particles. After that, we tested on 12 datasets with 200, 100 and 80 nanometer particles, which means that we also want to detect smaller particles. In that, we received an average count exactness of 87%, and as one could expect, this value decreases if we have smaller particles and decreases when we have higher disturbance rates. But we compensate some of the disturbances. The separation of contaminated and non-contaminated samples is another interesting thing. So if we have a look at our average dataset, so we average all the 12 datasets, we can detect 141 particles per 1000 images. When we, on the other hand, detect on background datasets, that means we have datasets without any samples in it, they just contain disturbances, we can detect 2 particles per 1000 images. This means that we can easily find a threshold basing on these datasets to separate contaminated from non-contaminated samples. As one goal I mentioned at the beginning was the fast detection speed. We will also have a look at this, of course. The total detection time that we could measure for one image passing the whole detection pipeline lied between 40 milliseconds and 300 milliseconds. This time depends mainly on 3 factors. One factor is the image size, so a small cutout of the whole image analyzes, of course, faster than the whole image. A higher number of particle candidates will also result in a higher computation time, as well as the number of actual particles. And if we have a look at the distribution of times, here in comparison between a dataset with few particles per image and a dataset with a higher number of candidates per image, we can see that the distribution changes. So the main aspect which changes is the temporal filter. The temporal filter is currently designed in a very sequential way, so each candidate will be taken and analyzed, and we expect that we can accelerate that when we parallelize the temporal filtering more. The last thing that I want to present to you is the future research and what we want to reach with the PAMONO-sensor. One thing that would be very nice to have is a model-based approach for new viruses. As for example, the new coronavirus has shown us, is that it is hard to train on datasets which you don't have. And we hope that with a model-based approach, we just could implement some functionality to generate new samples from the old characteristics and some physical properties of the new virus. We also want to use this device in the outside world, so not inside a laboratory, and therefore we have to compensate heavier disturbances than we currently do. There will also be some demand for higher mobility when we use it on site, and for that we have 2 options. One option, which was described in the paper below, is the outsourcing of calculations over mobile connection. So we could, for example, have many mobile devices which record some PAMONO images, send it to a server, and receive the results back from the server. Another option for more mobility is, of course, to use some embedded devices, which was already done for some parts of the PAMONO project. And we could use this knowledge to combine previous and current work to make a smaller version and a lighter version of the current net. Now that we reached the end of the presentation, I want to thank you for your time and hope that you learned something about the virus detection with the PAMONO-sensor. We will see each other on the Q&A session tomorrow if you have some questions about this topic. Goodbye.